for the invitation to CRM. We were here back in 2014 for a month, and we've always had a really great time being in Montreal. So today I'm going to speak on joint work with Kent Vashaw and Milen Yakimov. And so my talk will be based on these three papers. I must say that these three papers are really based on a lot of earlier work done by the people who are listed on the board and others too. So if I don't mention them at various times, know that they're still very important for actually doing this. So the idea is that we're looking at tensor categories. They need not be symmetric tensor categories. And we want to treat them like rings, like non-commutative rings. And that'll be the theme throughout the talk. And this is not a new idea. This was introduced by Paul Balmer for the symmetric case, where he used the tensor product structure like a commutative ring. And so I'll explain that later on. All right, so I'm actually getting older now. And so I've been giving these talks which are semi-historical. So I have to go back to kind of the dawn of time. So this concept is a very old concept, but it was introduced in the 1970s, and it sort of started off categorical representation theory in many ways. Right? It's a very, very sort of elementary concept. So what you do is you take a finite dimensional algebra, and then you take a finite dimensional module over that algebra, and then you take a minimal projective resolution. Okay, so a projective resolution where the kernels have no projective summands. And the idea is that you just want to look at the rate of growth of this projective resolution, right? And you want to know whether it grows linearly or grows quadratically or grows, via some polynomial. Okay, and there's a sort of a bound in terms of the dimension of the terms here. And so the smallest possible s is called the complexity, right? And one observation that you can make after you use this definition is that if A is self-injective, then the complexity actually gives you an invariant for projectivity. So the complexity is 0 if and only if the module is actually a projective module. Now, there's no guarantee that this number will actually be an integer either. The number could be infinite. Okay? All right, so should I say got it? It says something on.
Oh, don't worry about that. You
Don't worry about that. Okay, great. I think it can be, but for now, let's just define it as an integer. Okay. All right, so this is a Lie theory conference. So what I'd like to do is I'd like to use Lie theoretic examples. So if you want to think about the small quantum group at a root of unity, it just follows sort of in the same way. So this is just the characteristic P version where I just take the restricted enveloping algebra. So you take this restricted enveloping algebra, which is the quotient of the ordinary enveloping algebra. It's a finite dimensional Hopf algebra. You look at the principal block. It has two simple modules, the trivial module and a P minus one dimensional module labeled by this highest weight. And then what you can do is you can just take the minimal projective resolution for this. Right, and we know what the projectives look like in terms of their submodule structures, and you could just build the minimal projective resolution in this way. And so the trivial module is dimension 1, P0 is dimension 2P, the next one has dimension 4P, and then 6P, and so forth and so on. So here's the formula for the dimension. This projective resolution, or this minimal projective resolution, grows at a linear rate of growth. So the complexity is 2, okay, by the previous definition. The what? Oh, that's a characteristic of the field. Sorry, this is in characteristic P, right? Yeah. So, the complexity of the trivial module is 2, and that's not a coincidence. We know the dimension of the nilpotent cone is 2 also, right? And I'll show you why there's a connection in a moment. All right, now let's move on in history. So now what people wanted to do was they wanted to actually introduce geometry into the situation. So they were looking at these varieties, these affine algebraic varieties. They're also conical. And so they define them using annihilators, but I want to do this using localization because this will be more convenient later on. So the idea is that you take the cohomology of some finite dimensional Hopf algebra, and you assume that the cohomology ring is finitely generated. Okay, it's not known whether this is true in general, but for finite groups, it's known. For other cases, it's also known. And then you want to know that when you take X of any two modules, then it's going to be finitely generated over the cohomology ring. That's using the tensor structure. And then the way you define this variety is you just look at all primes inside the spec of the cohomology ring, which localize X of MM, and it's not equal to 0. Okay, so the localization is actually not equal to 0. So another way to define this is that R acts on the cohomology ring, X of MM. You could take the annihilator ideal. You can take the cohomology ring modulo the annihilator ideal, and then you can take the spec of that too. It's equivalent to this definition. Okay, so for every module, you get a variety, and we call it the support variety. And what you can prove under these assumptions is that the complexity actually equals the dimension of this affine algebraic variety. And this finite generation assumption is really important. It's so important that there's a big conjecture by Ettinghoff and Ostrich for arbitrary finite tensor categories. So they conjecture that for arbitrary finite tensor categories, which could include arbitrary finite dimensional Hopf algebras, the cohomology will be finitely generated. And this condition here will also be true. Okay, so these two conditions are part of the Ettinghoff-Ostrich conjecture. And in the co-commutative case, this is a big theorem. It appeared in Invenciones back in the 1990s by Friedlander and Sussline.
What rating would you, if you have an arbitrary finite tensor category, what's the?
So you just look at the unit object and the unit object, you know, the sort of the Hom or X or whatever in that finite tensor category. You know.
What was your answer?
Oh, so you just take the unit object. So it's X to the trivial module, basically. So there's an analog in finite tensor categories. All right. So let's do a Lie theoretic example again. So again, you take the restricted enveloping algebra, which you can realize is what's called the first Frobenius kernel. It's equivalent. When you take the support variety for the trivial module, Janssen proved that you can realize it in terms of the p-nilpotent cone. So for GLN, this just means that you take the matrix to the pth power and you get 0. So it's a subvariety of the nilpotent cone. And so whenever you take a module for your algebra here, the subvariety is always going to live inside the nilpotent cone for the Lie algebra. Okay, so the nilpotent cone here comes up because of the cohomology ring. And we actually proved a conjecture of Janssen's that was formulated in the 1980s. And what this theorem now does is it actually says that the support variety of the costandard module is actually going to be the closure of some Richardson orbit. Okay. And it's prescribed by doing this little algorithm over here involving stabilizers. So from this theorem, you can actually compute the complexity out, and it's just going to be equal to twice the dimension of the unipotent radical of this parabolic. Okay, so this shows you that you can actually use support variety theory in Lie theory, and for certain modules, namely these costandard modules, which are very familiar to people, you can compute the support varieties and you can compute the complexity out that way.
Okay. What about the simple
modules? No, this is a good question. So for simple modules, assuming that the listed character formula is true, but we don't know that whether that's true in general, then the same thing holds. Okay. In the quantum group case, we can actually show this, but in the algebraic group case, it's still an open problem.
Sorry, if lambda is like a generic dominant, then it's
The whole thing, you get the entire p-nilpotent cone. So this stabilizer just measures where the weight is in terms of on the walls via the affine Weil group. Okay, so yeah. I don't want to get into all the combinatorics, but you can get the flavor from this theorem. All right, so what's the big idea? The big idea was introduced by Paul Balmer. And it's sort of an idea like any of us would like kind of come up with or think about. So you take a symmetric tensor category. So this category, you can take direct sums, which is like an addition. And then you have tensor products of modules, which is like a multiplication. So the idea is to think about this symmetric tensor category like a ring, right? Like a commutative ring. And so what do you do in commutative ring theory? You define a prime ideal spectrum. And that's exactly what Balmer did, was he defined a prime ideal spectrum for any symmetric tensor category. And what we did was, actually, before I say anything more, so in the literature, and you'll see this term done a lot, it's known as tensor triangular geometry. So if you see the word tensor triangular geometry, this is what he basically did, or what they're talking about, okay? And what we did was we wanted to understand the theory when you have a non-commutative tensor product. And it turns out some very, very interesting things happen in the non-commutative world. So the next part of the talk will sort of deal with going from categories. And what we're going to do is, because we're doing things like spec, we want to topologize. And we know that spec is what's called a Zariski space, right? So the idea is that we want to actually transport objects in the category to this Zariski space. And so in order to do that, you have to use something like support varieties. And Balmer calls this support data, all right? So what I'm going to do is I'm going to go through each of these concepts, and at the end, I'll show you how everything gets put together. Question?
So is this the same as like saying that we're taking spec of the Grothendieck chain, or is there like more structure?
No, there's more structure. I was going to say this later. I'm going to conduct like heresy at this categorification conference. I'm going to remove the K0. Okay, so no K0 here. Okay, but I'll show you that you have to be careful in doing this. All right, you just can't take arbitrary indecomposable modules. So that's where a lot of this theory will come in. That's a very good question. All right, so a more concrete way of thinking about this is you can take like the category of quantum groups, you know, and then, or a category for Lie algebras, and then on this side you should get the nilpotent cone back again. So this procedure should actually unveil the nilpotent cone for you in some way. All right, so I'm going to start with the basic definition of tensor categories. So this was actually done, I think, yesterday. So I'm going to start with the tensor category, and then I'm going to also assume that it's triangulated. Right, this is a very important property because it allows us to do things. You could do these constructions for any monoidal tensor category, but the triangulatedness allows us to classify things. All right, so let's start with some examples. You take a finite dimensional Hopf algebra. So you take you have the coproduct, you can make tensor products into modules. So you have the regular module category, and this actually appeared in Josh Sussenstock, the stable module category. So the way you introduce the stable module category is the objects are basically the same, but you look at morphisms which factor through projectives. Okay, so then the projective objects are 0 in the stable module category. And the important thing about this stable module category is it's actually a triangulated category. And so you have the stable module category for finite dimensional objects, and then this is sort of known as the compact part of the stable module category for infinitely generated objects. Okay, I'm not going to mention much about why you need infinitely generated objects, but you actually do in this whole game. Okay, so here's another example. So you take a commutative Noetherian ring, you could look at perfect complexes. So these are complexes of finitely generated projective modules. Okay, and these turn out to be tensor triangulated category. You're tensoring over R, and then inside of this, these are the compact objects in the regular derived category. Okay, so these two are sort of two motivating examples. All right, so as promised, we're going to do, basic algebra now. We're going to define ideals. Okay, so what is an ideal? It's a triangulated subcategory such that when I tensor on one side by elements of K, objects of K, with elements inside of the triangulated subcategory on either side, I get back inside of the triangulated subcategory. Okay, same definition as what you would expect. All right, so for the direct sum, we actually need a technical condition called thickness. So we don't want things to be just closed under taking direct sums, but we want them to be closed under taking direct sum ands too. So if a direct sum is contained inside of an ideal I, then each of the components has to be contained inside of I. That's a thickness property. All right, now this is the notion that you're probably fairly familiar with prime ideals. So this is called object-wise tensoring. So something is prime if the product is actually inside of P, then either one has to be into P. Either M has to be in P or N has to be inside of P. But in the non-commutative world, as maybe Tim will attest, you actually need another definition of primeness, where you actually tensor ideals together. Okay, and this is where we introduce this notion of primeness into the game, where if you tensor two proper thick ideals and they're contained inside of this P, that implies that one is either I is contained inside of P or J is contained inside of P. Okay, so this is sort of the ideal tensoring definition of primeness, and this is the object tensoring definition of primeness. And they are related. I should also mention that this new definition was introduced also by Buon, Krause, and Solberg too. They kind of introduced it, but didn't do too much with it. Okay, and so now what you want to do is you want to topologize the prime ideals. So you just topologize them sort of like you would with spec of a ring. Okay, so you define the closed sets in this way and to topologize the SPC. So SPC are all the prime ideals inside the ring. Now, you can also define the completely prime spectrum too, okay, using the object-wise tensoring. So this is what Balmer has. This is our sort of prime ideal spectrum. And it turns out that the completely primes always sit inside of the primes, all right? And so the problem in the non-commutative situation is that the completely primes are too small, right? You need actually a bigger space in order to actually say things, right? And that's why the other definition was quite important to introduce. Okay, any questions on this so far? Yeah, go ahead. No. Yeah, it's just completely in terms of objects. Yeah. Yeah. Okay, so the next thing I want to talk about are Zariski spaces. All right, so you're probably fairly familiar with Zariski spaces. If you take spec of a ring, in your commutative algebra class, you know that it has very, very nice properties. If R is a Noetherian ring, then spec is a Noetherian topological space, for example. So we're just sort of taking that property. And another property that you know about spec of a ring is that if you take any irreducible set, then it has a unique generic point. Okay, that's one of the important properties. So we just encapsulate those two properties in this definition, and that's what's called a Zariski space. And so, these are the examples. You can take spec of a ring. You can look at, if R is graded, you can look at the homogeneous prime ideals, and you could take proj, okay? So then that's also going to be a Zariski space. And then if you take an algebraic group, which is actually acting on the ring rationally, then you can take this, I think this was introduced in Emily's, the stacky quotient. And that's going to be actually Zariski space too. So now what's going to be important when working with these spaces is just some notation. And so what's going to be important? Well, what's going to be important are the closed sets, of course, and also the collection of subsets, the irreducible closed sets. So I just adorned everything by little, subscripts to sort of indicate what these things are. And the most important concept probably is the idea of specialization closed. So, so what this means is that you just can take arbitrary unions of closed sets. Okay, so if you take an arbitrary union of closed sets, it's specialization closed. That's the definition. Now, as we know, it may not be closed, right? But it turns out to still be an important concept. So we'll label all the specialization closed sets by XSP.
Are the points not necessarily closed?
Oh yeah, no, because you have generic points. Yeah, so now that turns out to be quite important. All right, so the next thing we're going to do is we're going to introduce support data. Now, I don't want you to memorize all this, so I'm not going to go through every single line, but the point about support data is it just has the properties of support varieties. So you basically want direct sums to go to unions. You want tensor products to go to intersections. You want it to be closed under the shift. You want, if you have if things are have a dual, then you want the supports to be the same, so forth and so on. Now, I have two versions of support data. I have WS1 and S1. So sometimes we use what's called weak support data. Sometimes we use the regular support data. That's not important in this talk, but I just wanted to indicate that, you could change axioms around just a little bit, modify them for your purposes. Okay, so this is the basic definition of what a support data is. The idea is that you take objects in your M delta C, or your triangulated category, tensor triangulated category, and you send them to subsets inside of your Zariski space. Okay, and that satisfies these properties. Now, there are two additional properties that will be important. We want the support data to detect projectivity. That's this property over here, S7. Okay. And we have another property in terms of realization. So if you take any closed set inside your Zariski space, you want to realize this as a support of some module. So this goes back to work of John Carlson, where he actually proved this for finite groups using the support variety for finite groups. Okay, so this is a property that's pretty familiar in support theory. Okay, so I have M delta C's. I have these triangulated categories. I have Zariski spaces. I have support data. And now we're going to put it all together. Okay, so we're going to stare at this theorem for a little bit because I think this theorem is quite important. It has kind of a long history. All right, so in the literature, you'll actually see this theorem in various guises. We have a version. So this is due to Bo, Kajar, and myself. So we use this for looking at least superalgebra representations and finding out what the Balmer spectrum is for GLMN. We have a non-commutative version of this theorem in one of our papers, in our first paper. And then Del Ambrosio also has a version of this theorem more in a topological setting. Okay, but I just want you to kind of get an idea of what this actually does. All right, so what do? You look at this compactly generated monoidal tensor triangulated category, okay? And the idea is you take a Zariski space and you want to actually find a support data which satisfies the axioms that I presented beforehand. So if you're able to find a support data which does the job, then you can actually classify thick tensor ideals in your category. And they're in bijective correspondence with specialization closed sets. When you think about it, it's kind of miraculous you can even do this, right? If you take indecomposable modules, you can't classify indecomposable modules. So in some sense, this is the best you can really do. is to actually classify thick tensor ideals. So certain triangulated subcategories of modules. And so this actually gives you a classification, and the classification is very, very concrete. Okay, so if you take a thick tensor ideal, you just take the union of the supports, and then you just use this definition over here to go backwards. Okay. And so you have actually this, beautiful correspondence, which allows you to go back and forth between specialization closed sets and these thick tensor ideals. So in some sense, you remove the K0 from everything, right? So specialization closed sets. So unions of closed sets, arbitrary unions of closed sets. So if I give you an arbitrary union of closed sets, I can give you a thick tensor ideal, and vice versa. Okay. Now, moreover, you can use this to actually give a homeomorphism and compute the Balmer spectrum this way. So this categorical spectrum that I had before, you can actually compute right on the nose by using the Zariski space. All right. So a lot of people in this game would like to know, what the Balmer spectrum is for certain categories, and we can do this by actually using this theorem. Okay. So this is just a recap of what we did. So you input a monoidal triangulated category. You have a perspective Zariski space. If there's a nice support data between the two, which satisfies the axioms, then everything's good. You know exactly what the Balmer spectrum is.
Is there like a converse result which says that you can always make a support data?
Yeah, there is. So, yeah, that's called the universal support data. We'll come to this later on. Okay, very good. Yeah, Balmer has a whole theory in his paper. Okay. All right. So let me work through some examples really quickly. All right. So suppose you take a finite group or a finite group scheme. So you could take a finite dimensional co-commutative Hopf algebra. You look at its cohomology ring, and then I sort of mentioned how to actually construct support theory or support varieties. So that's what we do down here. This is the old definition. This is actually a good support data, which does everything you want. All right. So it satisfies all the properties that I mentioned before. And so thick tensor ideals are in one-to-one correspondence with specialization closed sets in the proj of the cohomology ring. So what's really nice about this is that, beforehand, you take the category of representations for like a finite group, like characteristic P, and we knew how to do tensor products. We knew how to do all of these computations, and we knew something about the cohomology ring, but this actually ties everything together now. I mean, the cohomology ring is in the background in terms of the representation theory. Okay, and then if you take the Balmer spectrum, the categorical spectrum, it identifies with the proj of the cohomology ring. Now, okay, so that's a good motivating example, I hope. And now we'll do a more Lie theoretic special example of the motivating example. So you take GLN set of invertible matrices, you take its Lie algebra, and it turns out that when you take the cohomology of the first Frobenius kernel, it identifies with regular functions on the nilpotent cone. This is a result by Anderson and Janssen and Friedlander and Partial back in the 80s. So there's a result for the small quantum group due to Ginsburg and Kumar, which is rather similar, right? And it turns out that this is an example of the previous example. And so you can identify now the Balmer spectrum with the proj of the coordinate algebra for the nilpotent cone. So you can see the nilpotent cone actually comes up in this whole theory by using the cohomology over here. Coxeter number. Yeah. It's just like Ginsburg-Kumar. It's conjectured that this will actually hold for the small quantum group too. It's not yet proved that the Balmer spectrum for the small quantum group actually at a root of unity, Lth root of unity, identifies with this when L is bigger than H. Okay. If people know this ABG like equivalence of categories, this is all it's all sort of built into this. This is part of it. Okay. All right. So next thing. So it turns out that if you take spec of a ring, you'd like to recover it from a categorical spectrum, right? So we use that prior example involving perfect complexes. So when you take perfect complexes, you can actually define a support theory by just taking the homology of the complex and then localizing and seeing whether it's 0 or not. So this gives you the support data, and this support data satisfies all the axioms that we had before. And then you can actually say that the categorical spectrum over here identifies with the spec of a ring. So you can recover the spec of a ring using a categorical spectrum. And this was a theorem due to Thomason, a very famous theorem due to Thomason. Okay, so now I want to go to the non-commutative world. Let's see how we're doing. Okay, we're doing fine. All right, so I don't necessarily want you to like read all of this. Okay, so what do I want you to get out of this slide? So Benson and Witherspoon constructed a finite-dimensional Hopf algebra, which is non-commutative. Okay, using a smash product and then taking its dual. Okay, so there are a bunch of details in here, but that's basically the upshot of this, is that they constructed this nice finite-dimensional non-commutative Hopf algebra. All right. Now, this Hopf algebra was important because I should sort of preface this with a little short story. So Dave Benson was a colleague of mine for 4 years at Georgia. So he actually, I think he claims he hired me. So you can, whatever that means. So Dave would like, one of the things Dave liked to do was he liked to, when he talked math with you, he would like come up with these like really weird counterexamples. So counterexamples that were kind of surprising and shocking in some ways. So he loved to do this to people. And I would say that this is like one of them, okay? So the idea is that if you take the cohomological support that I defined before, all right, then he wanted to sort of show that, or actually Sarah and Dave wanted to show that the tensor product theorem does not hold. Okay, so this is actually the cohomological support variety information does not give you support data. That's what this statement says. That tensor products do not go to tensor products, intersections of varieties. Okay? All right, so they came up with this example. I think Dave was pretty pleased because he had stumped people for a while. And so it turns out that this example was around maybe for about 5 years. And then we worked on this non-commutative theory. And it turns out that we can reconcile this example. So when you take this particular algebra, okay, just like we had before, then you can actually classify thick tensor ideals. And you can compute the Balmer spectrum, but then you have to use the stack quotient over here in order to get an isomorphism. Okay, so you just can't take the ordinary cohomology ring and get an isomorphism between the Balmer spectrum, just like in the co-commutative case. For the non-co-commutative case, it's much more difficult and much more complicated. And so this gives an example of, or an indication of how you might be able to reconcile things when you go from commutative to non-commutative, co-commutative. And one of the things you have to do is you have to use the definition of prime ideal that I gave you beforehand, not the completely prime definition. So that helps to actually reconcile this particular example and to classify the Balmer spectrum. So now the question, there's a question that a lot of people have been interested in. So they've been interested in knowing when particular support data actually satisfy the tensor product property. So if you take the tensor product, the two modules, you want to know that's the intersection of the supports. So for finite groups and co-commutative Hopf algebras, this is known. this is actually a very deep result due to Friedlander and Partial and Friedlander and Petsova and others, and Carlson and Everin and Scott. So I think several of these papers appeared in Inventiones, for example, just to answer this question. The Everin and Scott paper definitely did appear in Inventiones. And so for arbitrary finite dimensional Hopf algebras, we know this is not true. And so the question is, when is it actually true? And when is it not true? So we actually give an answer to this, both a positive and negative answer. So I'll present two theorems. And the idea is that if you differentiate between the prime ideals and the completely prime ideals, then this actually gives you an answer for this universal support datum that Joel asked about beforehand. Okay, so whenever you have this monoidal triangulated category, you always have a universal support datum, which is given by this. Okay, and so if all the prime ideals are completely prime, remember, completely prime implies prime. If every prime ideal is completely prime, then you have the tensor product theorem. So what this shows is that when you differentiate the types of prime ideals, you can actually answer the tensor product question. So this approach is really nice because it sort of starts looking at how these support theories kind of differ involving various prime ideals, various types of prime ideals. And then if you have nilpotents in your category, so if you take an element, you tensor it, and then you get a projective module, which we know can happen, like in the Benson-Witherspoon example over here, then it turns out that not all primes are completely prime. So that means the universal support datum does not satisfy the tensor product property. And then with a little work, you can show that the cohomological support data does not satisfy the tensor product property either. So this theorem really reconciles what's happening with the Benson-Witherspoon example. So because there are actually nilpotents in this ring, and because you can actually show that prime ideals are not all completely prime, then you can actually say why this is happening, why the tensor product theorem is not working in that case. Okay. All right, so I have a couple minutes. And so now this is the last part of my talk. All right, so now for finite dimensional algebras in general, or arbitrary finite tensor categories, how do you compute the Balmer spectrum? I mean, is it possible to actually compute the Balmer spectrum in that case? And it turns out that we have a guess. So this is what I call our new and bold conjecture. So it involves a ring, this C lower T over here. Okay. So this is a subring of the cohomology ring, but it's not the entire cohomology ring. It can't be because we know they're counterexamples. So what our conjecture says that if you take a finite tensor category and you look at its stable module category, then there's a homeomorphism between the proj of this ring, right, and also the Balmer spectrum, the categorical spectrum over here. Okay, so in the case of finite dimensional co-commutative Hopf algebras, it would recover that result. All right, so I need to tell you a little bit about C of T. So we call this the categorical center. So R of T is the cohomology ring. Okay. And so this kind of looks a little like the talk at the end of the day, Emily Peters' talk at the end of the day, where you want a tensor on the left and you want a tensor on the right, and you want things to match up. And so basically that's the idea of this diagram. So we have M over here, it identifies with one tensor M and one tensor M over here. And you take an arbitrary element inside the cohomology ring, which you can realize as Homs from the identity to the shift, right? And so you can look at identity tensor G over here and G tensor the identity over here. And then you have this identification, and you want to look at all G's where this whole square commutes. Okay. And that forms a subring inside the cohomology ring. So not all elements actually satisfy this, but certain elements do. And the elements which actually satisfy this commutativity, we're going to call the categorical center. And so with this, we can actually prove this theorem. So if 1, 2, and 3 hold, then the conjecture is true. So 1 and 2 over here involve finite generation of the cohomology. And 1 and 2 will be true if Etinghoff and Ostrich, the Etinghoff-Ostrich conjecture is true. So if the Etinghoff-Ostrich conjecture is true, 1 and 2 will hold. And 3 is sort of the problem. Okay, we don't know how to reconcile 3 yet. In all known examples, you have to verify 3 sort of case by case or example by example. But we don't have a general way to actually handle 3 yet in general. But 1 and 2, if someone is really bright enough and can prove the Etinghoff-Ostrich conjecture, we can handle that. But like number 3 is still a little bit of a problem. And so once these 3 conditions hold, then for any finite tensor category, it'll identify with the proj for the central cohomology. What do we call this? The categorical center. Okay, so this actually agrees. So there are a bunch of examples due to Benson and Witherspoon, Benson, Plavnik, and Witherspoon, and also Negron and Petsova. They computed out various examples for finite dimensional Hopf algebras and their Balmer spectrum. And in every single example that they've computed, this actually works out. Okay, so there are no known like counterexamples yet to this. Okay, so let me stop here, and I thank you for your attention.
Thank you very much for the questions.
Yeah,
I'm so confused about these specialized closed.
Yeah, specialization closed sets, yes.
How can we think about them? Like, I don't know, they're just AN or something, what are they?
Oh, what are they?
Yeah, for the affine space.
You just take, okay, so if you take affine space, you're just going to take whatever topology you have. You just take arbitrary unions of closed sets.
Is everything?
No, I mean, you just, no, you just take, you just take, sorry. So you don't take arbitrary unions of all closed sets. I'm just saying if you take a closed set, that could be an arbitrary union. If you take 2 closed sets, a union of those is a specialization closed set. If you take the union of 3 of them, it's just let me just write it out. So you take it over some index set, okay? So just A sub I, okay? So that's what a specialization closed set is.
Just all the points are closed, right? So can you just pick an arbitrary set and then your index set through the points in the set and then
Yeah, so if the points are closed, yeah, that's the thing. But if they're not, then could be different. I know it's kind of weird, but because the topology I think is really coarse, I mean that's what allows you to do a lot of things with this theory. So yeah, go ahead, Tim. Or was it Tim or yeah, go ahead.
Yeah, so if I understood correctly, in the symmetric case,
Yes.
the co-prime, the constitutive primes and primes are the same.
Mhm.
Is there any interesting example, non-symmetric, with this condition is still holding?
Where it still holds?
Yeah.
Yes. So if you take, yeah, that's a good question. So if you take U zeta B, okay, so small quantum group, B is the Borel, okay, then it holds.
So for the Etinghoff vector, I'm curious like how we find the support variety. Is it like via Tanaka duality for example, or like via the support data like the one category here?
For my last over here. So all you do is to define the central cohomological support data, you just define it like you would with the cohomology ring. So you take all prime ideals in that ring, which localize to, which don't localize x to MM to 0.
And is that like in any way related? Like if I take, for example, the finite tensor category and like Why I can divide together like some finite-dimensional Hopf algebra.
Hmm.
If I take like the support variety, like the classical support variety of this Hopf algebra, is it the same as?
Yeah, I believe that's true.
Let's expand again.
Okay.